Thank you for having me here. I'm really excited to share with you the homology representation of the moduli spaces delta 2n. So the outline of my talk is going to be, I'll go through quickly the constructions of MTROP-GN and delta GN, just so that we are all on the same page about notations and some conventions. And then I'll say a few words on the theory of symmetric delta complexes to give an alternative description for the tropical moduli spaces. And then after that, I will specialize to the genus 2 case. And finally, I'll say a few words on some work in progress. So usually at this point, I have a few slides or this one slide to convince people that tropical geometry is interesting, but I think we are all here, so we probably agree that tropical geometry is interesting. But I'll still say a few words on the history of these spaces that I'm looking at. So the space MTROP-G that parametrizes tropical curves of genus G, the definition, the construction that I'll be talking about today, it was first introduced by Bernetti, Mello, Viviani back in 2011 as an effort to construct the tropical Torelli map. And the analogous moduli space parameterizing genus G and with marking with unmarked curves was introduced by Caporaso in the 2013 paper. And however, even before these constructions, in tropical geometry came around, the spaces they define actually have appeared in other contexts of math way before that. And for example, MTROP-0n is the space of phylogenetic trees, as just mentioned and discussed a lot by Anthea. And it was first defined in 2001. And even before that, we have this delta GN, in particular delta 0, and it was studied by Robinson and Whitehouse as the space of fully grown trees back in 1996. And not only did they study the homotopy type of this space, they were able to compute the representation of Sn afforded by the homology of this space induced by the action of permuting the unmarked points. And this delta GN is a smaller tropical space that sits inside this bigger moduli space MTROP-GN. And why do we study these tropical spaces? Well, one reason is that there has been an identification proven by Abramovich, Caporaso, and Payne in 2012 of this delta GN with the boundary complex of MGN bar, the Dillon-Mumford compactification of the algebraic moduli space. And in particular, this implies that a lot of information we study here in the tropical space can be transferred to become knowledge of the algebraic moduli space MGN. And in particular, this identification identifies the rational homology of delta GN with the top weight cohomology of MGN. And this identification is furthermore Sn equivariant, which means it respects the action of permuting markings. And so I guess that's one reason why we really want to study this tropical space here. And so now I'll quickly go through the constructions. And I'll start with the definition of an unmarked weighted graph. And such a graph is a triple GWM, where G is a finite connected multigraph. And multigraph means that we allow parallel edges and self-loops. And W is a weight function that assigns a non-negative integer to every vertex. And finally, the marking function M assigns the markings 1 through n to the vertices of our graph. And we impose a stability condition on our weighted graph by requiring at each vertex v 2 times the weight plus the graph theoretical valence and plus the number of markings, and this quantity to be greater than 2. And so we mentioned that in this multi-graph, self loops are allowed, and in particular, self loops contribute twice to the graph theoretical valence. And we define the genus of such a graph to be the first Betti number of the graph itself plus the total weights. And in particular, we can visualize the weights sort of as miniature loops around each vertex. And that is another way to sort of understand, well, why we take 2 times the weight to in the stability condition, because whenever we have a weight at a vertex, then we can always consider it as a small loop. Cool. And to package all these information in the category, we can define this graph category, gamma GN, where the objects are the stable unmarked weighted graphs of genus G that we just defined. And the morphisms in this graph are going to be edge contractions and isomorphisms. And isomorphisms in the category are graph isomorphisms that respect the weight function and the marking function. And edge contractions are usual graph theoretical edge contractions. But now with the weights and the marking, whenever we contract an edge, we would take the union of the markings on the 2 endpoints for the new vertex, and we would add up the weight. And one special type of contraction is contracting a self loop. And to be consistent with our interpretation of weights before, well, whenever we contract a self loop, to retain the genus, we're going to add 1 to the weight. So I usually draw weights as a number and with a little circle around it. And just some terminology, we say 2 graphs to have the same combinatorial type if they're isomorphic in this category, gamma GN. And in practice, we often, instead of considering the bazillion objects in this category, we only consider the combinatorial types, which are the isomorphism classes. And so we will only be dealing with finitely many objects in this manner. So now a tropical curve is really just a marked stable graph, weighted graph of genus G together with a length function that assigns a positive real number to every edge. And we further define the volume of a tropical curve to be the total edge length. And I will quickly go through the construction of MTROP-GN by working through an example. And so roughly speaking, how we're going to go about the construction is that first we enumerate combinatorial types in the graph category gamma GN. And once we have all the combinatorial types in this category, we're going to assign to each combinatorial type a quadrant in R to the number of edges in that combinatorial type. And then finally, we're going to glue all these cones together along the faces via the morphisms in the graph category gamma GN. So glue according to morphisms in gamma GN. And so let's actually see an example together. Well, our step one is to enumerate combinatorial types in gamma GN. And so let's look at the graph category gamma 1, 2, and then see what combinatorial types are in there. Well, I'm also going to list the combinatorial types in a poset where the covering relations are given by edge contractions. And sitting at the bottom of this poset is the unique graph with only one vertex with no edges. And so we're gonna have all the weights and markings. So I draw weights as a number with a little circle around it, and the markings are rays with the numbers at the end. And now sitting above this combinatorial type, we can have a combinatorial type that looks like this with two vertices, one edge, and the left vertex having weight 1 and the right vertex having weight 0 with the two markings. So often if the vertex weight is 0, I will omit writing the 0 next to it. And another combinatorial type sitting above is this fish graph with one vertex, a self loop, and two markings. As thinking about these two, we have this combinatorial type, which also contracts to the fish graph, and this graph here. So notice that these are the only stable combinatorial types in gamma 1, 2. And now, once we have enumerated the combinatorial types, we're going to assign a cone to each of them. And let's first look at this combinatorial type here. Well, if we name the edges A and B, then we're going to assign this positive quadrant in R2 to this combinatorial type, where each point in the quadrant corresponds to a particular length function on the combinatorial type. And similar to how Anthea discussed of how we graphed, these cones together, well, we're going to glue the boundaries according to the maps in the morphisms in gamma GN. And in particular, we identify having length 0 with contracting that edge. And what that means is that gluing to the positive y-axis, we're going to identify the cone with the combinatorial type with edge A contracted. And that gives us the combinatorial type corresponds to this one. And similarly, this face is going to be identified with this combinatorial type here. And the vertex and the origin is always going to be identified with the unique graph with only one vertex. And now let's consider the other max cone in our space. Well, here things are a little bit different because there is also because there is an automorphism on this of this graph by swapping the two edges. And we said that we were going to glue these cones according to the morphisms. So in particular, what this means in gluing this particular quadrant is that we're going to fold the quadrant in half and only consider the quotient by this action of swapping the two edges. And what happens to this face? Well, it corresponds to contracting either one of these two edges, and that corresponds to this fish graph. And the middle, this the line that we fold across, it corresponds to the combinatorial type or the tropical curves where these two edges attain the same length. So 1 and 2. And again, the origin is our one vertex to graph. So finally, to put everything together, we will have this green face, and the blue one, the purple, and finally the red origin. And so this will be our mtrop 1, 2. And we can easily see that this construction works for general G and N. And now to find this smaller tropical moduli space delta GN, we take basically the cross-section where we normalize this space by asking for the part in mtrop GN that parametrizes those tropical curves with total length 1. And so back in this picture, what that corresponds to is this smaller space. And so naively speaking, why we might want to look at the delta GN more is that mtrop GN is always going to be a cone with the cone point defined by this one vertex to graph. And therefore, if we want to study the topology of these tropical spaces, then mtrop GN is going to be quite boring. But on the other hand, we can instead consider this compact space sitting inside that captures all the interesting topology. And so that's one naive way to think, well, why we really want to be looking at delta GN in this picture. And another thing I mentioned at the beginning is that there is a natural action of Sn on our space by permuting the markings. So we can actually see that action and the how its homology carries this action as well. So in this case, we see that there is an S2 action on our space by permuting these two markings. However, if we look at any of our combinatorial type, then we see that it does not care about the S2, in particular, the transposition of 1 and 2. And so what that tells me is that if I take the homology of this space, well, first of all, it's contractible. And so there's only going to be one non-trivial homology. And furthermore, that's going to be affording the trivial action of S2 because we see that the space is insensitive to the transposition. And so for the rest of the talk, I'll be mainly focusing on delta GN and in particular in genus 2 and this Sn action on it. And what do we know already about this setup? Well, as I mentioned at the beginning, in the 1996 paper by Robinson and Whitehouse, they computed the homotopy type of delta 0n. Well, this result was given in Anthea's talk as well. We know that the homotopy type of these tropical trees is a wedge of spheres. And they also computed the Sn representation afforded by the top degree homology to be something, to be this particular representation of Sn. And fast forward to 2020, Chen, Glatius, Payne proved that delta 1n is actually homotopic to a wedge of spheres as well. And they were able to compute the homology representation afforded by the top degree homology as well. And so at this point, there are probably two natural questions or directions to ask, to go. which is, well, first, is it true that the delta GN is always going to be a wedge of spheres? And, when happens in genus 2? So those are kind of like the two natural things to ask. Well, unfortunately, delta GN is not always going to be a wedge of spheres. Chen in 2015 showed that all the homology lower than the top 2 degree is going to vanish. However, she further computed for n up to 8 the dimension of the top 2 degree rational homology, and for n at least 4, we see non-vanishing in both top 2 degrees. And so what that means is that it's not going to be a wedge of spheres, unfortunately. And my goal for this paper is to promote this table here to be SN representations. So I want to be looking at the top 2 degree rational homologies as SN representations. And I'll show the computational result upfront, and we see. And here I'm writing the character of the top 2 degree homologies up to n equals to 8 as a direct sum of irreducible representations indexed by partitions of n. And so it looks quite messy. And for the rest of the talk, I will say a little bit of how we were able to make this computation and maybe what to go after this. And before I can tell you how exactly we computed these homology, I'll first introduce the theory of symmetric delta complexes. Well, we set the notation n bracket to be the set from 0 to n, and we define the category I to have objects bracket P for OP at least -1, and we set the morphisms to be injections. So this is the category Fi of finite sets and injections, or I guess it's a full subcategory, skeleton subcategory of the other category. But since we're sort of like using it in a different context, we're calling it a different name. And a symmetric delta complex, it's a functor from the opposite category of I to sets. And how we think of these symmetric delta complex is we can think about its canonical geometric realization by thinking the image of bracket P to be the set of P simplices. And the image of the injections are going to tell us how these P simplices glue together. And this construction is very similar to an ordinary delta complex construction. And in the usual story of delta complex, we would take the category to be a little bit smaller of these bracket P with order preserving injections. And that corresponds to, in the usual construction of delta complex, we would require face gluing to preserve the orientation of the faces. And one implication of the fact that we're including all injections is that, well, now we're going to be including, for example, permutations as well. So that means given a P simplex is where we have the freedom to glue it back together to itself. So already we can see how this corresponds to the construction of the tropical moduli space, because since in the tropical picture, we are able to glue a cone to itself by automorphisms. And we see that this construction of symmetric delta complex allows that to happen, whereas a usual delta complex would not tolerate that self-gluing. And so indeed, we can describe delta GN as a symmetric delta complex where the image of bracket P is the set of combinatorial types with exactly P plus 1 edges together with an edge labeling or an edge ordering where we assign, the edges from 0 up to P. And how we're going to map the injections. Well, whenever we have an injection from P to Q, well, we look at the map going the other way from X, from all the combinatorial types with Q edges down to combinatorial types with P edges. And this map is given by contracting corresponding edges that are outside the image of this eye. And the upshot of giving this alternative description is that there is a cellular chain complex associated to every symmetric dotted complex that computes the singular homology of its geometric realization. And so now we actually have a tool in our hands where we can enumerate, for example, the generators and look at the chain groups and actually compute the homology. And maybe I'll just say what goes in, like what's the P chain group in this chain complex. Well, over Q, let's just do everything rationally. So it's generated by these combinatorial types with the edge ordering to get but modeled by some relation, where the relation is given by if we have two different orderings on the same graph, on the same combinatorial type, then there is a permutation on the edge set that takes one ordering to another, right? And we're going to take that permutation and relate these two different ways of ordering the edges by the sign of that permutation. And so pi is in, I guess pi takes tau to tau prime. And the differentials in this chain complex is going to be like an alternating sum of all the different ways we can contract a single edge. And there is also a relative version of this cellular chain complex. And what that means is that we can identify subcomplexes and do relative homology, just like how we would want to do that. Okay, great. And at this point, we might be tempted to just go ahead and use this cellular chain complex. However, these chain groups, as G and N get even a little bit bigger, these chain groups are going to explode because there are just so many combinatorial types. And so there are some structural results that help us simplify and instead of doing the full chain complex, we can work with relative homology and only deal with a small number of generators. And one such structural result is proven by Chen, Glatius, Payne in their 2020 paper. So assuming G is greater than 0 and 2G minus 2 plus N is greater than 0, then the closure of the locus of the tropical curves with bridges is empty or contractible. And in particular, it's only empty if and only if Gn is 1 and 1. So in our case, since we care about the genus 2 case, then this bridge locus is always empty. And a bridge in graph theory means an edge in a graph whose deletion will disconnect the graph. And here we use it in the same sense. And at this point, maybe I will say a little bit of what combinatorial types go into the bridge locus, because so that we can see when we are doing the relative version, the relative homology, what generators we would still need to consider. And the bridge locus really contains a lot of different combinatorial types, which, upon first looking, don't have bridges, because we're really taking the closure with respect to edge contractions. And in particular, of course, we would include all the combinatorial types with a bridge up front. For example, any combinatorial type that looks like this. And similarly, so we have bridges. And whenever we contract a bridge, we're gonna get a cut vertex, which is defined to be a vertex whose deletion disconnects the graph. And so everything with cut vertices is going to be are going to be in the bridge locus as well. And what else will be in the bridge locus? Well, if we define the core of a weighted graph to be its smallest subgraph that contains all cycles of G and all vertices with positive weights, then in fact, every graph whose core is a proper subgraph will be in the bridge locus as well. So let's see an example. So if I just draw, say, maybe I'll take 4 markings here. And now if we have a combinatorial type like this, then the core of this graph is going to be this dumbbell combo type. And so we see that basically by taking the core, we are cutting off all the trees that grow out of that grows on the core. And so whenever the core of a combinatorial type is not equal to itself, we're going to have these trees, floating around. And whenever we have a tree, then there's going to be a bridge. And so we see that these are all bridges. And therefore, when we consider in our relative homology, we really want to be looking at those combinatorial types whose cores are exactly themselves. And another big family, big subcomplex sitting inside the bridge locus is the repeated marking locus. And what this contains are all the combinatorial types where the marking function is not injective. So whenever we have 2 markings sitting at the same vertex, then that's going to be contained in the bridge locus as well. And how we can see that is by taking, say, any repeated marking, and we see that it has an uncontraction where we can grow out a tree. And therefore, we see that it's in the closure of the bridge locus. And now if we consider the genus 2 case, then, so here I've listed the 7 combinatorial types in gamma 2, 0. And what do we know about the bridge locus? Well, if we consider some arbitrary gamma 2n, then the core of any combinatorial type in gamma 2n is going to look like one of these, I guess, 6 combinatorial types, and with possibly the edges subdivided and with markings sprinkled on top of them. And so now if we look at delta 2n rel, the bridge locus, then we will actually not be seeing any of the combinatorial types whose core look like anything in this yellow circle with the edges possibly subdivided. And one way to see that is also that, well, in this combinatorial type, we see this bridge in the middle, and no matter how we subdivide the edges, we're still going to have a bridge. And so everything below this combinatorial type is going to be sitting in the bridge locus. And furthermore, we argued that the repeated marking locus would be inside the bridge locus as well. And so that tells us when we consider this relative chain complex, the chain groups are really generated by combinatorial types that looks like this theta graph, and with the edges possibly subdivided with markings at those vertices, but none of those vertices would have more than one marking on it. And so it's got, it's generated by combinatorial types that look like, say, 1, 2, 3, 4, 5, stuff that looks like this. And that's already a big simplification, but we have even more simplification that we can use. And another structural result was proved by Chen in 2015 that says for n at least 4, the cyclic theta complex is Q homologous to a point. And what goes in this cyclic theta complex? Well, it contains the bridge locus, first of all. And furthermore, it contains all the theta graphs. So since earlier we said that outside the bridge locus, we have all these theta types with markings here and there. Well, it also contains those theta combinatorial types where the markings on the theta graph can be found on a single cycle. And some examples would be if we have 1, 2, 3, and 4, then we see that all these 4 markings can be found on this single cycle. And so this big subcomplex here is Q homologous to a point. It's actually not contractible because in considering integral homology, it actually has torsion. And so that's another interesting geometry to look at. But here, for our purposes, since we're only looking at rational homology, we might as well discard this entire complex. And so at this point, how does the relative cellular chain look like? Well, now we have the cellular chain delta 2n rel C2n. And we said that we only have these theta types where the markings are not on the same cycle. And let's, so theta types with markings not on a single cycle. So we can actually look at an example, a small example for n equals to 4. So when n equals to 4, how can we distribute these markings on the theta graph? Well, without them landing on a single cycle. Well, there are, I guess, 2 general shapes. One, we can have combinatorial types that look like this, and we can label these markings 1, 2, 3, 4. And there are 4 truths to which is 6 non-isomorphic combinatorial types that have this way of kind of distributing markings on the 3 theta edges. So combo types. And these form the generators for C6, or let's see, 1, 2, 3, 4, 5, 6, 7, yeah, for C6. And so that tells us C6 is 6-dimensional. So it's 6-dimensional. And another way of distributing the markings without them falling on a single cycle looks like this. And so we have 1, 2, 3, 4. And there are 4 combinatorial types that looks like this. And so that tells us C5 is generated by 4 graphs and is 4-dimensional. So now we have successfully simplified the chain complex to a very short chain complex that looks like this. And now we can actually be more specific here and see how this differential works. And let's see, so I'll quickly draw these. So the 6 combinatorial types are given by these 6 combinatorial types, and on the bottom we have let's see. These 4, so 1, 2, 3, and 4. And I only labeled certain markings because we're only considering isomorphism classes of combinatorial types. So in particular, we're able to, whenever 2 combinatorial types are related by an isometry of the theta graph, then they should be considered the same element in our or the same point in our space. And we see that if we contract, and the differential here is really contracting edges. And so we have map that goes from like this, and have this, that have 2 and 3, 2 and 4, and 3 and 4. And so we will end up having this 4 by 6 matrix. That's our D. And the entries are going to be, in this case, 1 or -1 or 0. And there are some signs given by the relation that we talked about earlier, where whenever 2 edge labelings are related by some permutation, then the two elements are related by a sign. And here, I guess, implicitly, we have the edge labelings. So these are the generators, I guess I should say. So, or these are bases of C6 and bases of C5. So one can see that where we wouldn't be able to write down a specific matrix for our differential here, and therefore compute the homology in both the higher and lower degrees. And furthermore, we can see how we might compute the SN representation using this basis, because we would be able to permute these markings and write these chain groups as SN representations and analyze the situation together with this differential to compute the SN representation structure on the homology. And in general, for general N, we would have 3 terms in our chain complex. So in degrees n plus 2, n plus 1, and n. And their dimensions do get pretty large as n grows, even after OR simplification. For example, when n is 8, these chain groups can have dimensions to say like 60,000. And that's why the computations do take a while. And our strategy for computing the SN representations is exactly like I discussed, where we look at each chain complex, each chain group, and we compute their SN representation structure and analyze the differentials. And in particular, we can describe the top degree homology pretty easily as a sub-representation of this chain group. And so we can look at the data again. And as I said, it's quite messy, but there are some patterns, but I think some of them are not yet published. But one such pattern, but we do know some patterns for example, for the trivial representation and the sign representation. And in particular, we can see that if we just look for the trivial representation, then we have a trivial representation in the top degree homology for 2, and then the bottom homology for 4, and then again top homology for 6, and bottom homology for 8. And so, but however, our goal eventually would be to actually give a formula for, say, the top dimension homology representation. And so at this point, maybe I'll say a few words on some work in progress and how we would like to tackle that. And if any of this smells familiar, please give me a pointer, or I would love to discuss. And now recall that in the complement of the bridge locus, we were looking at all these combinatorial types on the theta graph where the markings are not allowed to collide. And that looks a lot like the configuration space of endpoints on the theta graph. However, they are not exactly the same, because first of all, when we consider the configuration space on any other space, we would fix, for example, the graph and then sprinkle points on the graph. But in the tropical setting, well, these theta graphs, as long as their total edge length is 1, it doesn't matter, like we can still alter our graphs. And another difference is that in configuration spaces, if we have, say, 2 combinatorial types, if we have 2 configurations that looks like 1, 2, 3, and 4, and 2, 1, 3, 4, then they would be considered different points in this configuration space. However, in the tropical setting, these 2 would be considered the same point since they are related by an isometry of the graph to itself.
Also for generic edge lengths? Only for particular edge length, right? Otherwise,
Yeah, only for particular edge length. And so, yeah, exactly. So how we want to tackle this is by considering a homotopy equivalence to a particular like fixed theta graph with particular edge length, and then mod out the space by the isometry of that theta graph. And once we do that, we can consider a slightly larger space that allows the markings to collide, but without growing out any trees. And this technique is used by people who study configuration spaces as well, because once you allow the points to collide, there is a natural stratification of this slightly larger space by the partition lattice, basically, where each set partition gives us the way of like how those markings can collide. And once we have this stratification, we can apply this technique developed by Dan Peterson of a particular spectral sequence, which computes the compactly supported cohomology of the open strata in terms of that of the closed strata. So in this setting, what we're interested in is the cohomology of the open strata stratum, where none of the marked points are colliding with each other. And in terms of, like a smaller, in terms of information on the closed strata where the points are indeed colliding. And those spaces are easier to compute because they can be, there is a homotopy equivalence to the configuration space, or really to the theta graph, to some power mod out by its isometry group. And so I guess that's how we want to tackle this problem, but then again, there's also the SN action on it, and there are a lot of details like entangled together, and so it's a route we're taking right now. And if this rings a bell, and please talk to me, and I would love to know more of configuration spaces and other ways people think about this. And so I think I'm gonna end a few minutes earlier, and thank you for your attention.